We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, our focus will be on elastic collisions, namely those collisions in which the only forces that act during the collision are conservative forces. In these collisions, the sum of the kinetic energies of the objects is conserved. We will find that the description of these collisions is significantly simplified in the center of mass frame of the colliding objects. In particular, we will discover that in this frame, the speed of each object after the collision is the same as its speed before the collision. Last time, we discussed the important topic of momentum conservation. In particular, we found that when the sum of the external forces acting on a system of particles is zero, then the total momentum of the system, defined as the vector sum of the individual momenta, will be conserved. We also determined that the kinetic energy of the system, defined to be the sum of the individual kinetic energies, is not necessarily conserved in collisions. Whether or not this energy is conserved is determined by the details of the forces that the components of the system exert on each other. Last time, our focus was on inelastic collisions, those collisions in which the kinetic energy of the system was not conserved. In particular, non-conservative work was done by the forces that the individual objects exerted on each other during the collision. Today, we will look at examples in which the only forces that act during the collision are conservative forces. In this case, the total kinetic energy of the system is conserved. We call these collisions elastic collisions. As an example, consider the collision we discussed last time with one modification. Instead of having the boxes stick together, we'll put a spring on one of the boxes as shown. The spring will compress during the collision, storing potential energy, and when it relaxes back to its original length, it will turn this stored potential energy back into kinetic energy. In this way, no mechanical energy is lost during the collision, so that the final kinetic energy of the system will be the same as its initial kinetic energy. We will now spend the rest of this pre-lecture looking at these elastic collisions in more detail. We will start with the example from the last slide. Knowing that neither the momentum nor the kinetic energy of the system will change during this collision allows us to write down two independent equations that relate the initial and final velocities of the boxes. We start by equating the total momentum in the x direction before and after the collision. Next, we equate the total kinetic energy before and after the collision. We've now obtained two equations containing 6 variables: the initial and final velocities of box 1, the initial and final velocities of box 2, and the masses of the two boxes. Therefore, if we know any 4 of these quantities, these two equations will allow us to solve for the other 2. For example, if we know the masses and the initial velocities of both boxes, then we can solve these two equations for the final velocities of both boxes. So far, so good. There is a complication, however, that will make the actual solution of these equations tedious at best. For example, if we solve the momentum equation for the velocity of box 2 after the collision in terms of the velocity of box 1 after the collision, and then plug the result back into the energy equation, we get a pretty messy quadratic equation that, with some effort, can certainly be solved. There is, however, a better way. Physics can rescue us from this tedious mathematical chore. Namely, if we solve this problem in the center of mass frame, we can avoid solving any quadratic equations. We can then determine the final velocities in the initial frame by simply transforming the velocities in the center of mass frame back into the initial frame. We will perform this calculation on the next slide. Here we see the collision as viewed in the center of mass frame. We've labeled the velocities in this frame with an asterisk. Now, the total momentum is conserved in any inertial reference frame. What distinguishes the center of mass frame, though, and what simplifies the calculation, is the additional constraint that the total momentum is always 0 in the center of mass frame. Consequently, the single momentum conservation equation has become two equations, one for the initial state and one for the final state. To see how this constraint simplifies the problem, we will multiply and divide each term in the energy equation by the appropriate mass. The result of this operation is that each term now is proportional to the square of an individual momentum. We can now use the momentum equations to write each side of the energy equation in terms of the square of the momentum of just one of the particles. In fact, we see that the magnitude of the momentum of each of the objects individually is now also the same before and after the collision, although the direction of each one has changed. In other words, when the collision is viewed in this reference frame, the speed of each object is the same before and after the collision. This is a very important and useful result and provides us with a very simple strategy to solve any elastic collision problem. We will work through such an example on the next slide. We will now work out a one-dimensional example that demonstrates the use of the center of mass frame in elastic collisions. Here we see a 2-kilogram box sliding with a velocity of 5 meters per second in the plus x direction on a horizontal frictionless surface toward a 3-kilogram box, which is initially at rest. The boxes collide elastically. Our job is to determine the final velocities of both boxes in this reference frame, which we will call the lab frame. Our first step is to transform this problem to the center of mass reference frame. In order to make this transformation, we need to know the velocity of the center of mass in the lab frame. Now, in Prelecture 10, we determined that this velocity was just equal to the vector sum of the individual velocities weighted by the fraction of the total mass each object carries. Plugging in the values for the masses and the initial velocities, we find that the center of mass is moving at 2 meters per second in the plus x direction. We can now use this value for the velocity of the center of mass to determine the initial velocities of the boxes as viewed in the center of mass frame. We know that the velocity of an object in the center of mass frame is equal to the velocity of the object in the lab frame plus the velocity of the lab frame in the center of mass frame. We know the velocity of the lab in the center of mass frame must just be equal to minus the velocity of the center of mass in the lab frame. We can now find the initial velocities of both boxes in the center of mass frame by simply adding numbers that we know. Here we see what the collision looks like as viewed in the center of mass frame. Note that we have used the result from the last slide that the magnitude of each individual velocity after the elastic collision is equal to its value before the collision in the center of mass frame. Our final step is to transform our results to the lab frame. We will do that and offer some general comments on the next slide. Here we see our results for the final velocities in the center of mass frame. We will now transform these final velocities from the center of mass frame back to the lab frame to finish the problem. We can make this transformation by simply adding the velocity of each object in the center of mass frame to the velocity of the center of mass in the lab frame. When we make these additions, we see that after the collision, box 1 moves with speed 1 meter per second in the negative x direction, and box 2 moves with speed 4 meters per second in the plus x direction. You can verify, using these values, that both momentum and energy are indeed conserved in this collision. If we now replace the values for the masses and the initial velocities of this problem by their symbols and follow the identical procedure, we arrive at the general expressions for the final velocities of any two objects undergoing an elastic collision under the assumption that the second object is initially at rest and that all motion is in one dimension. We can learn a couple of interesting things from these equations. First, if the masses are the same, we find that the final velocity of the first object is 0, and the final velocity of the second object is just equal to the initial velocity of the first. In other words, the objects trade roles. Second, we see that the final velocity of the first object changes sign if m2 is greater than m1. In other words, if the first object is lighter than the second, it will bounce back. If, on the other hand, the first object is heavier than the second, it will continue in its initial direction with a reduced speed. The last example assumed that the motion of the colliding objects was constrained to one dimension. We found that knowing the masses and the initial velocities of both objects was enough to completely determine the final velocities. We will now extend this analysis to two dimensions by considering the collision of objects on a frictionless horizontal surface without any constraint that the motion is along a single axis. An actual example of such a situation might be billiard balls colliding on a pool table or pucks colliding on an air hockey table. We will start by making the simplification that the mass of both objects is the same and that one of our objects is initially at rest. Even in this restricted case, we can see that the final velocity vectors cannot be determined from a knowledge of the initial velocity vectors alone. The animation shows very clearly that the final directions depend on the orientation of the objects when they collide. If the collision is head-on, the final velocities will be along the x-axis, just as in the previous example. But if the collision is not head-on, the final velocities can have y-components as well. So what can we say about the final velocities in these cases? Well, just as in the previous example, we get the simplest view of the collision from the center of mass reference frame. Prior to the collision, we see the objects approaching each other head-on, and afterward, we see them leaving the collision pointing back to back with exactly the same speed they had before the collision. The one parameter that is not determined from the conservation of momentum and energy is the angle between the initial and final velocities of one of the objects. Indeed, this angle can vary all the way from 180 degrees in the case of a head-on collision to 0 degrees in the case where the objects simply miss each other. We conclude with a brief discussion of the main points of this prelecture. First, we determine that if the only forces acting during a collision of two objects are conservative forces, then the kinetic energy of the system, defined to be the sum of the kinetic energies of the colliding objects, is conserved. We call such a collision an elastic collision. Second, we determine that the elastic collisions could be most simply described in the center of mass frame of the colliding objects. In particular, in this frame, the speed of each object after the collision is the same as its speed before the collision. The collision may cause objects to be deflected through some angle in this frame, but their speeds will always remain the same.